Hello, this is Scott from Optics Realm. It's September 2011. Today I want to talk about some tricks in ZMax using solves to get a solution quicker. These were inspired by some papers written by Dave Shafer and shown to me by a coworker. So this coworker of mine, Dan, he read these papers, two Dave Shafer papers on aberration theory. Great titles, by the way: A Spectrum of Techniques for the Perplexed and the Meaning of Life, written in 1985. These were nicely distributed by Optical Research Associates. They've since been bought by Synopsys. They write the software Code 5, and this was done at the International Design Conference in 2010. There's an article on interviewing David Shafer. This is a picture of him here. I recommend checking that out. It's an interesting read. Dave has a fantastic way of writing in using plain English to describe lens design as opposed to drowning you in equations. Dan implemented these a different way than I would have. I would have used the merit function in ZMax. Dan used surface solves, and it's pretty cool. It's cool enough that I wanted to record a quick video about that. We're going to use the Double Gauss to show this demonstration. I'm going to go through a little background history on how the Double Gauss was formed, how it was designed and evolved through the years. But I need to talk about concentric, and concentric means having a common center. So if we've got a concentric lens, as is drawn here, the front radius and the back radius share a common center of curvature. Said another way, the front radius equals the back radius plus the center thickness. Domes are very commonly made of this, and you gimbal about the center point here. You can be concentric about the aperture stop. So if this is your aperture stop here, these surfaces are concentric about that surface. The other term I want to talk about is aplanatic. Aplanatic means zero spherical aberration induced from an optical surface. There are three cases where you're going to have zero spherical aberration. Two of them aren't very interesting, and those are when your object or image is on the surface, where your object's on the surface, or they're at their center of curvature. The object and image will be at that center of curvature. Not very interesting cases. The other case, and it's called the aplanatic case, that's when the surface increases or decreases the convergence of your beam by a factor that is equal to the index of refraction. Well, what does that mean? So in this case, your virtual image distance equals your radius times this ratio of indices of refraction. So if we have a beam coming in, a focusing beam coming in, this is the ray, this is the marginal ray for it here, it's going to focus, we'll project it forward, it's going to focus at this point here, and this is a distance I. So here's this I. This is the surface here, radius of curvature, here's the center of curvature, and that's this in this equation. If you're in air, where this initial index of refraction is 1, your radius is going to equal your virtual image distance divided by your index plus 1. Now, this also satisfies the Abbe sign condition. I'm not going to go into that here, but needless to say, this implies that you're going to have zero coma for a small field of view. So let's talk about the evolution of the Double Gauss. The Gauss was initially, it kind of evolved over the years. So it started with a singlet, and then it was bent to reduce spherical aberration. And then to reduce color, you came up with the crown and the flint. And a lot of these I'll be going over in my Optics Realm video tutorial series. And then Gauss, who's pictured here, which I took from Wikipedia, he proposed an objective in 1817 where he controlled coma by splitting this airspace in the achromat and doing bending here to minimize coma. Now, coma is a field aberration. There's two sources for this. They're great. A History of the Photographic Objective by Kingslake, and also Wikipedia has a great write-up on this. So how did it get its double name? Let me just go back and say the Gauss is an objective. It's an airspace objective where the crown and flint are bent for minimum spherical. Alvin Clark, who's pictured here in this Wikipedia picture, in 1888, he realized that if you make this symmetric about an aperture stop, you're going to get rid of the three field aberrations, astigmatism, coma, and distortion. And just some historical significance here. His father was Alvin Clark, and he built a 9.5-inch Gauss objective, not the double, just the crown and the flint. And he commented that it wasn't as well corrected as he would have expected. So how did this evolved further? So again, this is 4 elements: crown, flint, flint, crown, symmetric about an aperture stop. Paul Rudolph took the next step, and in 1896 he wanted a good aplanant, meaning a good lens that had low spherical aberration. What he did was he split this second element here into 2 components, and he had a buried surface in here, and he found that if he varied this inside radius or curvature, he could affect and change color without drastically affecting the other aberrations, and it's still symmetric from front to back. These lenses here, they're cartoons, they're not anything real. So let's go to ZMax, and I kind of want to show how this is done. So what I have here is a bunch of plane parallel plates. Let's say, as some young lens designers do, which I used to do, you start with plane parallel plates. We know we want a double Gauss. We're going to start with a singlet and a doublet, and we're going to pick these back surfaces up from these over here. And you can see I've done that. Now I've added radii here to show indeed that they are being picked up. So this front radius here is picked up on this back radius. And I selected some O'Hara glass. So this is just a general starting point. I did your typical focal length, kind of lens geometry constraints, back focus, color, and field curvature. Now I've put a dummy surface in. The aperture stop is floating, and I want to show, the aperture stop is really out front. Okay, so it's this first surface right here. But I come back, and this allows this aperture stop to float through the system. Now why would we do that? Turns out you need to do that for these surface solves, which I'll be showing you here in a sec. So let's say I'm not doing surface solves here. I know this is what the double Gauss looks like, and let me just show you my performance metrics here. I've got ray intercept curves over field. This is the on-axis ray intercept curve, distortion, which I'm not controlling, field curvature and color, and MTF at 5, 10, and 15 line pairs. It doesn't look good because it's a bunch of plane parallel plates. But I've set this up here, and let's just optimize 50 cycles. And we can see this evolve over time. It's going to freak out and do some crazy stuff, but what do you expect from 2 plane parallel plates? We can see the MTF is starting to creep up. We're starting to come into focus. Again, a focus term in the ray intercept plots is a pivot about the origin. We're starting to reduce color here a little bit. You can see the double Gauss form is coming in. The lenses are thick. It's kind of nasty. Again, I put a 1 millimeter entrance pupil diameter here. It's very slow. It's not very realistic. So here's kind of our starting point. Now I'm going to go to image space F number. We're going to give it some speed to the lens. Now it's going to look kind of nasty. We'll do another set of 50 cycle optimization. And you can tell that it's got an achromatic solution here. There's a little bit of field curvature. I've constrained it not too heavily. You can see that back here, just the Petzval radius curvature. And you can see the system is starting to come in. We're 25 cycles through. As you'd expect with field curvature, it's focusing at some off-axis field point, balancing the aberrations across the field. I only have 3 fields: on-axis, edge, and the typical 0.707 zone. So you can see here, if you optimize from plane parallel plates, you think you're going to get the double Gauss, but you really don't. You get these backwards curved surfaces here. We're achromatic, and our ray intercept plots are about 100 micron spot diameter. We've got some performance in terms of MTF. Now let's go to this other approach. Let's just, by example, let's put a solve on this. I'm going to put a concentric surface about surface 2. Now why surface 2? Surface 2 is our aperture stop. Okay, so that changes the lens here. And I'm going to make this back surface here aplanatic. You can see aplanatic. And it changes our lens. It gets us a starting point. Let me pull up my performance here. can see I've got, and look at that. Off the bat, I already have some MTF. So it saves a lot of optimization time. Let's optimize it. I'm only going to give it 10 cycles because we've got a closer starting point. So it's met some criteria. It's kind of gotten us there. Now I'm going to open it up. Again, that was a very slow beam. Let's give it an F. We'll make it F4. And I'm only going to optimize it another 10 times. And let's see what happens. And now you can see the form is coming in. It's looking like a double Gauss. Now your spot sizes are much larger than just blind optimization. And we're not achromatic. We don't have a double color crossing. Again, this is focus versus color. So what I'm going to do is I'm going to turn off these solves. I'm just going to make them variables. And I'm going to re-optimize, and I'll just pick 50 cycles, and we'll see if we get in. You can see the scale is coming down. Sorry I didn't show you what the shape of the on-axis field point looks like. But it is coming down. Let me turn off the update. Turn off the update. There we go. And we're still a little too large. Let me do more optimizations. Let's just let it rip, let it go automatic. You can see the merit functions coming way down. And we've got about the same spot size as the other optimization. Here your surfaces are not concentric about your aperture stop. You're still getting, the balancing of the field aberrations. You get one sign of field aberration induced over here and the opposite out over here, so they somewhat balance out here. So this is roughly a 50 micron, plus or minus 50 micron spot. We have okay performance. We go to this other case. We've got okay performance, but it's got more of your typical double Gauss shape. So I just wanted to show you that. And finally, Taylor Hobson broke the symmetry in 1920, and he took out a British patent, and this spawned like hundreds of double Gauss patents. So let's just take this system here, and we're going to break all this symmetry and see how this comes up. I need to keep my back focus, and you can see the merit function is dropped in half. Okay, 100 iterations is more than enough. We've dropped our spherical aberration. We've got a little astigmatism, a little distortion. MTF has come up. We're essentially diffraction limited. Well, look at that. I've got some negative airspaces in there. Let's redo that. I'm sorry. There we go. And technically this is too big, but you get the point. It's bringing aberrations greatly down. This is Scott from Optics Realm. You can contact me on opticsrealm.com or Gmail, scott.sparrow@gmail.com, Twitter, OpticsScott. Appreciate if you stop by and say hello or give me some grief or call me stupid or whatever. Anyways, thank you for listening and have a good day.